So welcome back. This lecture will be handled by Dr. Narasimhadhan. Just introducing Narasimhadhan is a faculty in the department. He received his BE from the Electronics and Communication from Andhra University, MPhD in Signal Processing from University of Technology, Guwahati, and PhD from Electrical Engineering in University of Science, Bangalore. Since 2014, you are a faculty here.
13, yeah.
Associate professor. He was mine contemporary in University of Science as well as here. So his research interest is in medical imaging, medical image processing, and computer vision, deep learning, and pattern recognition. So I request Narasimhadhan to take over.
And thank you, Raghavendra, for a brief introduction of mine. So today we will have a basic or introduction to the pattern recognition, a basic class for the pattern recognition. So you have been working with the deep learning for some time back. Okay. Have you ever thought about the basic building block for the neural network? So today what we are going to do is that we are going to look at the basic building block for the neural network. So that is the design of a two class classifier or two class linear classifier. Using least square method. So we are going to see this topic, and this is the basic building block for the nonlinear classifier, such as the neural network and deep learning, deep networks. So what I do is that I just take the example and illustrate how you can design the two class linear classifier, using that data. So the data we take, for simplicity, what we do, we take a simple data that you know. So we take, in the example, we take 3 images. What are the 3 images? The data, the 3 images that we are going to take. Out of 3, we see 2 images, right? 2 images belong to the benign class. You say benign class. Let's say it belongs to class 1. Let's say you have 3 medical images. Out of 3 medical images, you have two images which belong to the benign class, and the one image belongs to malignant. Let's say that this is a class 2. And we already studied about the feature extractions. We have studied about how you can take the GLCM features, right, from the images. What are the GLCM? The gray level co-occurrence matrix features. What those include? Those features include energy, autocorrelation, and many more features, right? So let us consider only one single feature. Let us say we are considering only the energy feature. Energy feature from the GLCM features. We are only considering a single feature. We are not going to consider other features. Only we are going to consider a single feature. Let's say we are extracting the features. There will be an extractor to extract the energy feature. So we extract the feature from the given images. Let's say the energy of the two benign images are, let's say the first image feature is, let's say for the first image we have the 1 unit. Let's say, we don't get into actual what do you call, right? So we don't look into the specific measurement of this, but you say that the energy of the image is 1 unit. Okay, first image energy is 1 unit. Okay, the second image, the 2 unit. Now the third image, let's say the third image, the feature is, the energy of the third image is 3 units. Okay, we have extracted the features. Now, this feature, the first image feature belong to this feature, the first feature that you see here, right? This one feature value belongs to which class? Class 1. And the second image, right? The 2 value here, the 2 feature value belongs to, again, the class 1. Let's say the class 1 is labeled as 1. Okay. Then we have another feature, the 3, which belongs to, let's say the class 2. The class 2 labeling is a -1. And these are the feature values. The feature values, and these are the labels. Now we got the features from the images that we have taken. What are these images? These are the images, 3 images. Out of 3, 2 are from the benign class and 1 from the malignant class. Let us depict these feature values in the feature space. We have something called feature space. How many features we are taking here? We are taking only a single feature. Now the feature space is a one-dimensional space. Since we are taking one feature, your feature space is a one-dimensional feature space. So let us depict these points on the feature space. Let's say this is the variable, the feature variable, which takes the energy of the images. Now, at x equal to 1, what is that we have? What is, when I say x equal to 1, this feature value belongs to the class 1. Let's say the class 1, right, is represented like this. is represented like this. Now, x equivalent to 2, when I say x equivalent to 2, x equivalent to 2, right, value, feature value, this belongs to which class? Class 1. Let's say the class 1 is represented like this. Now the third feature, what is the third feature value? 3, right? 3 belongs to class 2. Let's say this is this, right? So in the feature space, the distribution of the features like this. What we have shown here is the distribution of the feature values. How many features values we have? Right? We have 3 feature values here, and we have depicted. Okay, we have put these feature values in the feature space. Now we define a classifier now. By looking at this, the feature space, now we can define a classifier. I can define the classifier like this. Now my classifier is this. What is my classifier is? My classifier is h of x. H of x takes, h of x gives you a 1, right? It will give you a 1. 1 represents the class 1. If what, right? If it is equivalent to 1, if, can I say this? If x less than 2.5.
Why can't we take 3? Less than 3 also is class 1.
Yeah, you can take any point. See, by looking at the feature space, you can take this point to classify to separate the 2 classes. These 2 feature values belongs to class 1, and this one belongs to class 2. I can put a threshold. I can put threshold here, or here. I can take any threshold and I can define the classifier. I can define the classifier like this. The h of x is equal to 1 if x less than 2.5. You can take, this is called the threshold. You can take any threshold between this. Now, it is equivalent to -1 otherwise. Now, if the test data comes, now we have not used any processor to design this. What we have done here is that we have looked at the feature space and we have defined the 2-class classifier. We have defined the 2-class. We have not used any procedure, to find the threshold. By looking at the feature space, right, we have designed, come up with a 2-class classifier. Now, if the test data comes, let's say you are given an image, unknown image, it may be a benign or it may be, the malignant. Now, given an image, right? Let's say you are given an image. The first thing what we need to do to use this, we need to extract the feature, right? What is the feature value? Maybe it can be anything. Let's say it is equivalent to 4. Now what the classifier says? By looking at these feature values, we already defined a classifier based on the feature space. Based on the data available to us, we have defined the classifier. We have defined the classified based on the data that are with us. Okay, so this data is called the training data. For your information, this data is called the whatever the data we have here to train, right? This is called the training data. Now, by looking at the training data, we have defined the classifier here. Now, it's a time to test the classifier. But the classifier classifies correctly or not. It may misclassify, it may, classifies correctly. Right? So how do you check? We need to keep, right, some of the data as a test data, which has the labels. Okay, right? Let's say this, you are given unknown image, we don't know the label. Now, we ask, the classifier to take the decision. We give this image, first, we give it to the feature extractor. The feature extractor will extract the feature, and the feature value given to the classifier. What the classifier says is that, right, if this is the feature value, the classifier says that this image belongs to, this image belongs to, H of 4 belongs to what? Plus, this belongs to class 2. Yeah, it gives you -1. -1. It gives you -1. So practically what you do, you keep some data for the validation. Before you test the classifier with the unknown data, what you have to do, you have to keep some data, some part of the training data for the validation. Okay. Right? In general, I can define the classifier like this. In general, h of x is equivalent to 1 if a1x plus a0 is greater than 0 and h of x is -1 otherwise. In general, why I am saying in general? The function that you see here is just x. What kind of function is this? The threshold that we have kept here is the 2.5. In general, since we are into one-dimensional, right? We are looking at the one-dimensional feature. So in general, the function that you see here can be something like this. And the threshold, right, without loss of generality, you just keep the threshold is 0. So this is the definition that you see for the two-class linear classifier for one-dimensional space. For 1D, you say, right? 1D. And this function that you see here is called the discriminant function. This function is called what is this called? This is called the discriminant function. Why we call this as a discriminant function? It discriminates the two classes. It discriminates this function, say like, right? This function is called the f of x is called the linear discriminant function. Linear discriminant function. What if, suppose let's say you have n feature values. If I have n feature variables, how you define the classifier, two-class classifier? How you define that? In general, for the, right, for n-dimensional case, for the n-dimensional, for n-dimensional case, you define the classifier like this. How you define is, let's say you have n feature variables, x1 to xn are the feature variables. Is equivalent to 1 if what? If what? In the general case? In the general case, an xn plus an minus 1 xn minus 1 plus, yeah, right, so you have the a naught is, and this is equivalent to minus 1 otherwise. Can you put it in, can you put that in vector form? Can we put that in vector form? I can put that in the vector form. How do I put? I can define, this is a definition. I can define the two-class linear classifier as h of x. The x is a vector whose elements are x1 to xn. Is equivalent to 1 if W transpose x plus a naught is greater than 0 and the classifier is minus 1 otherwise. Where W is, what is this W? What is this W? Yes, so this is you can say A1, A2 to AN, A2 to AN. Right? Is that correct? X1, W transpose is that. So this one, right? So what is the W transpose X now? If you know, you can define like this. W transpose is that, right? Transpose of this vector, and X is the, where X is, what is X here? What is X? X1, X2, is there, right? But you have to look at it, you have to satisfy, we are saying this, right? So we have to, when you take the dot product between this and this, it should come like this, okay? Right? So is this correct? So this is actually the definition of the two-class linear classifier, and this is the building block for the non-linear classifiers. This is the linear classifier, and this is the building block for the non-linear classifier. And in the literature, what is this called? This is called this is linear classifier. A special case of this is called the perceptron. We know that the perceptron is the building block for the neural network, building block for the CNNs. So you can use the CNN as a nonlinear classifier. Now let us look at, we have started with the example. but we have different, somehow, we have got the classifier, but this classifier we have not derived using any of the method. What we have done here is that we just have looked at the feature space and we have defined like this. Now, is there any method, any formal method with which you can get the two-class classifier? What do you mean by getting a two-class classifier? For the given data, what is that we have to do? For the given data, we need to train the classifier, right? What do you mean by training the classifier? For the given data, the training means getting the parameters of the function. This is my function. It's a function of w comma x. X is the input that you give, and w, which characterizes the linear function here. And finding a linear classifier for the given data is nothing but getting the parameters which characterize the linear function. Right? Now we have this data. Can we get the parameters A1, A0? Why we are taking this? Because the data that we have considered here is of one-dimensional data. So if it is one-dimensional data, what is the linear classifier? This linear classifier, this is a general linear classifier for the n-dimensional. For the one dimension, the linear classifier is this. Using this training data, we need to get these parameters. Using this data, we need to train the classifier. The training of the classifier means getting these parameters. There are many ways to get these parameters. But one of the method you can use is the least square method. Can we apply least square method to get these parameters? Yeah, we'll apply least square methods to get these parameters. We already have some kind of classifier here. But what we have done to get this classifier, we have looked at the feature space and we had defined this. We have defined something like this. We have taken the threshold, right? If x is less than 2.5, then we say that this is the feature value belongs to class 1. But now if I use the least square method, what is the change in the two-class classifier that we get? The change is this threshold value will be changed. The threshold value will be changed. You see that we use the least square method, and you see that the threshold that we are going to get is a different one. Here, we just looked at the feature space and we have defined this. We have set up the threshold, right, and we have defined the two-class classifier. But if you apply actual method, if you apply least square method, what is the threshold that it would give? Can we go ahead? Can we see there? Can we apply the least square method? How many of you know least square method here? How many of you know least square method? Okay. So you don't require linear algebra. You can, if you know linear algebra, it is very easy to understand. But okay, if you don't have a linear algebra background, no problem. I'll try to make you understand. Okay, with the simple mathematics. It's easy. It's not difficult you to understand this. So we have defined the classifier, two-class classifier like this. Here, this function is a linear function, and we have put threshold here. If I substitute x equal to 1, ideally what is that you need to get here? We need to get a positive value. Ideally we need to get, if I substitute x equal to 1 here, what is that I have to get? I have to get 1. If I substitute 3 in this, what should I get? I should get, this must be negative value. Okay. So, ideally, right, since we are keeping threshold here and, we expect this, this function to give a -1. Okay. So, when I substitute x equal to 1, what should I get? When I substitute x equal to 1 in this function, what should I get? 1, right? 1 I should get. If I don't get 1, what is that? There would be error. Okay. So the error is this. This would give you, this supposed to get, if it is 1, then 1 minus 1 is 0, right? There is no error. But we don't know that this would give you 1 value. There would be error. This is the function, my function. I substitute value. There is no guarantee. It need not that, it would give you 1 value here. If it doesn't give 1 value here, then there will be a error, right? So the error is this. Now generally what they do, they'll take like this error. No, right? So what they take is square. Okay. No, this is the error for x equal to 1. What if x equal to 2? What is the error? This minus 1. Okay. If I substitute x equal to 3, what should I get? I should get the -1. If I don't get -1, there would be an error, right? So the error is we have 3 errors. Then what do? We add up. Okay, you add up. Then what we have to look for? There is error, right? So it's called the error function. Let's say this is called the error function. Right? So you can say this is the, what is W here? What is X here? Okay, let's say this is the error function. Right? We got the error function. Now we have to minimize this error function with respect to what? We have to minimize this function with respect to A1, A0. These are the parameters which characterize the linear function. The error must be minimum with respect to this. This is my error. What we are looking for is the minimum of the sum of the squares with respect to A1 comma A0. You are looking at the least of you are looking at the least of the squares, sum of the squares. So it's called the least square. It's called the, right, least square. So you are looking at the, right, if I say this problem is called the least square problem, right? So you try to minimize with respect to A1, A0. That would give you the parameters that would give you the minimum of this, right, are called the least square, method parameters. Now, how do we minimize this? We don't require, high-fi mathematics. We don't need to need to do. Have you done optimization course? No, fine. Optimization course. Okay, no problem, right? If you have not done, no problem. You can easily understand. So how do you minimize this? How do you minimize this function? This is a function of two variables. How do you do that? When you have the function which is a function of the two variables, what we do? We already seen this in the minimization of this in 11th and 12th, right? So somewhere we have seen this, right? What do you do actually? We take the partial with respect to the partial of j with respect to a1, right? And the partial of j with respect to a0, and then equate to 0. What is that we have taken here? We have taken the gradient of this function, and we have equated to 0. So we have to take the partial of this with respect to a1 and equate to 0, and take the partial of j with respect to a0 and equate to 0, and solve we get, when I do this, I get a linear equation. If I do this, again I would get another linear equation. Can you work out this? Anyway, I have results. Okay, you don't need to do that. I have, so you can try at home, but I will give you straight away the results. Okay, at least I'll give you the linear equations. Okay, so why do you get the linear equations here? Why do you get linear equations? Because the equation that you see is a quadratic equation. If I take the derivative of that, what is that you get? Linear equation. So two linear equations you get. So you will have the two set of equations, right? Now you solve those two equations. I'll give you straight away what are those equations. So what are those equations? Equations are this. One is 28a1 plus 12a0 is equal to 0, and then the other equation is 24a1 plus, other equation is, probably you would get something like this, 12a1 plus 6a0 is equal to 2. So you get a two set of linear equations. One is this, second one. Now can you solve this? What do you get? You know, right? How do you know how to solve the two set of equations, linear set of equations? Right? It's easy, right? We don't have any problem. So what is that? What are the A1 and A2? A1 is equivalent to, I'll give straight away. Okay. Minus 1 and A0 is 7 by 3. So these are the parameters that we got for the linear equation, linear function. Okay. Now you define. I will define, right? We already defined what is a linear classifier. The linear classifier, we defined something like this. Sorry. This is equal to 1 if A1x plus A0 is greater than 0, and this is equal to minus 1 if otherwise. Now you substitute the values A1, A0 in this, and what you get is h of x is equal to 1 if minus x plus 7 by 3 greater than 0, and this is minus 1 otherwise. Okay. Right? Now we just have to do some manipulations here. Okay. Then you can define h of x is equivalent to 1 if x, can you tell me x from that, x less than seven by 3, right? Is that correct? Is equal to minus 1 otherwise, right? Sorry, otherwise. Now by using the least square method, we have got the classifier is like this. But can you compare this with the previous classifier that we have got by looking at the feature space? Can you compare this classifier with the classifier that we got just by seeing the feature space? I'll just erase this, okay? Now we have a feature space, something like this. We have a feature space something like this, and by looking at the feature space, we got the h of x as h of x is equal to 1 if x is less than 2.5, otherwise, right, minus 1, otherwise this. You see that, the difference? By looking at the feature space, we got this. But now you see that, but what is the difference here? What is the difference between this classifier and that classifier? Both are, both gives you the, correct classification. But what is the difference between this and this? Here, there would be a change in the threshold? Yeah, yes, right? So there will be change in the threshold value. So we have, put, somewhere here threshold, but least square method gave us a different threshold. A different, approach would give you a different threshold. If I use, perceptron algorithm, there's something called, perceptron algorithm. If I use a perceptron algorithm to train your linear classifier, your threshold would be something different. Both classifier classifies the training data correctly. What is the training data here? The training data is this, right? Can you see, both classifier classifies correctly the training data? If I substitute, right, this is my training data. Substitute x equal to 1. What the two classifier says? This is a one classifier, this is other classifier. Both classifiers would say the given feature value belongs to class 1. And if x equal to 2, both classifier says class 1. 3, both classifier says this feature value belongs to class 2. And this is the building block. Now what I do is that I'll define a classifier something like this. What I do is that I say I just apply a sigmoid function. Right, to the linear function. The sigmoid of or for the 1D case, right? Okay. You know very well about the sigmoid function. How many of you know about the sigmoid function here? What this gives you? If I plot the sigmoid function versus this function, okay? The sigmoid of how this would be, how the sigmoid function would be. What is this sigmoid function? This is this sigmoid function is equal to 1 by 1 plus e power minus this a1 x plus a naught. Sorry. We have to do this, okay. This is my sigmoid function. When this function value is 0, what is the value of the sigmoid function? What is sigmoid function value? If it is 0, if this is 0, what is the sigmoid function value? This one, right? Which is equivalent to, let's say, this one is 1 minus, maybe right? So 1 by 1 plus e power minus a1 x plus. Now, if this is 0, what will happen? This would be 1. 1 by 1 plus 1. How much? Huh? 0.5. Okay, 0.5. No, if this is infinite, what is that? If this is infinite value, what is that unit would give you? If this is infinite, e power minus infinity is a 0, and what would you get is, you would get a 1 value. So at infinity, 1 value, at minus infinity, what is that you get? You're saying, you know, 0, right? So how the function values, if I plot, if I depict, you know, all the function values, how the graph would be? The graph would be something like this, right? So it's like, you know, it tends to 1. Okay, it goes to 0, and you know, eventually gives you the value of 1. Okay. Why do you want to do this? Why we compress? See, what we are doing is that we are compressing the values, the value of the linear function. We are compressing the values to 0 and 1. Now I define a classifier differently. Right? What is that I would do is that now h of x is equivalent to the classifier takes class 1. Okay, the class 1 is represented by 1. If the sigmoid of this is greater than 0.5. Now what is the threshold? See, we need to keep the threshold by looking at the function, the values of the sigmoid function. Now it is, what is the range of these values? 0 to 1. Where do you keep the threshold? At 0.5. So what you say that the classifier takes, right, 1 if the sigmoid, right, of this is greater than 0.5, and this is a -1 otherwise. So sigmoid function more of gives you the probabilities. It gives you the values in between 0 and 1. You know, right, the probability values always in between 0 and 1. So it would give you the probabilities. Now you are looking at the probabilities and taking the decision. You are looking at the probabilities here. For the given feature, I substitute here. I know how to get, A1 and A0. I substitute, for the given, x, I get, this function value. If this function value is greater than 5, what I would say is that, I would say the x belongs to 1. The x belongs to class 1. What does that mean? If for the given feature value, if the probability is high, what the classifier says? The classifier says that the x belongs to class 1. If the probability, if this value is less than 5, means that if the probability is low, then the classifier says that the feature value belongs to class 2. Now the interconnection of these classifiers would give you what? If you connect in a specific way, what you would get? If the interconnection of these two classifiers would give you, there is a linear classifier, still it is a linear classifier because it can, gives it, it separates, the classes linearly. Though you applied, sigmoid function. Sigmoid function is used to convert the values, into probabilities, right? But the sigmoid function plays a key role, in getting in neural networks. Already told you that the building blocks for the nonlinear classifier, right, are the linear classifiers. You interconnect the linear classifiers with this function, you apply the sigmoid function at the output of each and every linear classifier, and you connect these linear classifiers together, then the whole network, the whole classifier acts as a nonlinear classifier. At the whole network, or you would say that the whole network is considered as the neural network. Okay. We'll stop here. I don't want to get into if time permits, we'll again meet. I am going to teach you convolutional neural networks, and then if I get chance, if Raghavendra gives me time, then I will talk about the GANs, PCAs, autoencoders. So many more I talk about. Now, if you have any doubts, you can ask. Do you have any doubts on this?
Suggestion each
See, if you want to understand, take a simple problem and try to design. Okay, so like what we have done here. What I have done here, we have taken simple data, and I have designed the classifier. Say, take a simple, always simple. Look at simple data, and then try to design. Then you will understand many things. And what we do is that generally we don't understand the basics. Then we look at the hi-fi things. So what I say is that understand what are the building blocks. These are the building blocks. And if you understand these things completely, then you will understand the bigger things. So you always try to understand everything in terms of mathematics. If you have a good mathematical background, you will understand many things. Try to understand everything in terms of mathematics. Okay, thank you.